Open any flight tracking app right now, find any long-haul flight crossing an ocean, New York to London, Los Angeles to Tokyo, Sydney to Dubai, and look at the route. It curves, dramatically, noticeably, in a way that looks wrong, like someone drew the route with a shaking hand. But here is the thing, that curve is not a detour, it is not a mistake, it is not inefficient. That curved line on your screen is actually the shortest possible path between those two cities, and the reason why reveals something about the shape of the Earth that most people understood in school and completely forgot the moment they stopped thinking about it. Here is the problem with maps. Every flat map you have ever looked at is wrong. Not slightly wrong. Fundamentally, unavoidably, mathematically wrong. When you take the surface of a sphere, which is what the Earth is, and flatten it into a rectangle, something has to stretch. The areas near the poles stretch dramatically. Greenland on a standard world map looks roughly the same size as Africa. In reality, Africa is 14 times larger, and the same distortion that makes Greenland look enormous makes straight lines look straight when they are not. On a flat map, the straight line between New York and London passes over the Atlantic Ocean through roughly the middle latitude. It looks like the obvious route, the direct route, the shortest route, but draw that same line on an actual globe. Stretch a piece of string between New York and London on a physical sphere. The string curves upward, over the North Atlantic, closer to Greenland, closer to Iceland, much further north than the flat map suggested. That curved path on the globe, the path the string takes, is called a Great Circle route, and it is shorter than the straight line on the map by hundreds of kilometers. Because on a sphere, the shortest distance between 2 points is never a straight line on a flat projection. It is always a curve. But the Great Circle route is only half the answer. The other half involves something invisible, a river of air moving at speeds of up to 300 kilometers per hour at altitudes of 9 to 12 kilometers above the Earth's surface. The jet stream. Jet streams are fast-moving bands of wind that flow from west to east across the planet, driven by temperature differences between the equator and the poles. They shift in position and intensity with the seasons. They meander, they strengthen and weaken. But they are almost always there, and they represent an extraordinary opportunity for any aircraft flying in the right direction. A transatlantic flight from New York to London flying with the jet stream behind it can reduce its flight time by up to 2 hours compared to flying against it. On a flight that burns tens of thousands of litres of fuel, 2 hours represents hundreds of thousands of dollars in savings on a single journey. This is why eastbound transatlantic flights, New York to London, are consistently shorter than westbound, London to New York. The jet stream runs east. Eastbound flights ride it. Westbound flights fight it, or route around it. The curved path you see on the flight tracker is not just the Great Circle route. It is the Great Circle route adjusted in real time for the position of the jet stream. Pilots and dispatchers calculate the optimal balance between the geometrically shortest path and the meteorologically fastest one before every single flight. So the next time you pull up a flight tracker and see that curved arc crossing an ocean, you're not looking at a detour. You're looking at a navigator's solution to two simultaneous problems: the geometry of a sphere and the invisible rivers of wind that cross it. The shortest path and the fastest path, combined into one line. That curved route is not the plane going the wrong way. It is the plane taking the only way that actually makes sense.